Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Every breach starts with something small. A trusted login, a missed alert, a system no one thought could matter. Here, we follow the incident. How it began, how it moved, what broke under pressure, and what security engineering and business teams should learn before the next one. Because the next attack will not wait for a perfect plan. Now, let's follow the evidence.
Good morning. Welcome to Cybersecurity Under Pressure. Real attacks, real lessons. Today's Friday, July 3rd, 2026. Shout out to our friends in the United States. What happens when the technical detail of ransomware in industrial control systems meets the boardroom reality of operational uptime? This story answers that.
It really does. It's a perfect storm.
Yeah, it is. Because we are here to dive deep into the incredibly precarious intersection of 5G technology, legacy industrial systems, and, that relentless, crushing pressure to maintain operational uptime at literally all costs.
Right, because uptime is king.
Exactly. And, you hear about 5G, and if you were like most people listening to this right now, you probably just think of your smartphone.
Oh, for sure.
You think about faster movie downloads at the airport, or, lower latency when you're playing a mobile game or something.
Which is exactly the marketing narrative that telecom companies have spent, billions of dollars pushing to the consumer market.
Right, the commercials with the fast cars and the glowing blue lines.
Yeah, exactly. It is a highly sanitized view of what the technology actually is and what it's doing.
Right. But what we are really talking about today is what happens when that wireless frontier collides with multi-million-dollar industrial operations.
Real heavy stuff.
Yeah, we are talking about factories, marine ports, massive automated warehouses. We are looking at a fundamental re-architecting of how the physical world is controlled by digital systems.
And it is a collision that, quite frankly, most organizations are entirely unprepared for, completely blind to it.
Really? Even the massive ones?
Oh, especially the massive ones. If you look at the transition from traditional, heavily wired operational technology environments, what we generally call OT, to this brave new world of industrial 5G, it is framed in the industry as this massive frictionless leap forward.
Right. Just snip the wires and suddenly everything is better.
Yeah, exactly. And to be fair, in terms of sheer capability, it is amazing. But structurally, it is a fundamental re-architecting of the attack surface.
Which is terrifying. But, I completely see why a board of directors would be seduced by it, though.
Oh, absolutely.
If you are sitting in the boardroom, the pitch for 5G is just absolutely intoxicating.
Yeah.
You are hearing all about incredible flexibility, less cabling, which means lower physical maintenance costs, right?
Right, because cables break.
Exactly. They break, they get run over by forklifts, they degrade over time.
Yeah.
And going wireless means faster deployment times. You're being sold on this seamless, real-time support for automated guided vehicles, AGVs.
Those are the little robots moving parts around.
Yeah, just zooming around the factory floor, dynamically avoiding obstacles, mobile robots reorganizing massive warehouses on the fly based on supply chain algorithms.
It looks like magic.
It does. Digital twins mapping out entire production cells in real time. It sounds like the ultimate operational utopia.
Yeah. It is a brilliant pitch. It looks absolutely spectacular on a PowerPoint slide in a highly air-conditioned boardroom.
But there's a but coming.
Yeah, there is a massive but coming. The dark reality, and this is what keeps security architects awake at night staring at the ceiling, is that by embracing all of that beautiful wireless flexibility, you are taking massive operational risk and shifting it directly into the radio layer.
Okay, stop right there. Shifting it into the radio layer.
Yeah.
What does that actually mean in plain English for the people out there running these facilities?
Okay, so it means you are taking critical control loops, the exact digital commands that tell a massive robotic arm to stop moving before it crushes a human worker.
Kind of important.
Highly important. Commands that used to be safely hardwired into a closed physical copper or fiber system, right? And you are literally broadcasting them through the open air.
Okay, let me try to put this into perspective for you, the listener. Imagine you're sitting at home streaming a movie on your Wi-Fi.
Classic scenario.
Right. Someone turns on the microwave or your neighbor's router interferes with yours, and suddenly the network gets congested. The screen freezes, that little circle starts spinning, the video buffers.
Very annoying.
It is annoying, sure. You might miss a crucial line of dialogue, but imagine that exact same buffering happening not to your TV, but to a massive, multi-ton mobile production asset on a factory floor.
Close, but that analogy actually misses the most dangerous part of the industrial equation.
Oh, how so? What am I missing?
Well, when your movie buffers, the streaming service just pauses. The stakes are zero, you wait 10 seconds, it comes back.
Right.
But in motion control systems, physics doesn't pause. Right? If a robotic arm carrying a 2-ton automotive chassis buffers or an AGV loses its control signal for half a second, the machine doesn't just politely freeze in midair.
Because momentum is still a thing.
Exactly. The safety logic usually dictates an emergency stop, or worse, if the signal fails entirely, the momentum just carries it forward blindly. That is not an annoyance. That is a catastrophic physical consequence.
So the tolerance for a glitch goes from, mildly frustrating to, we just destroyed $1 million of hardware and maybe hurt someone.
Exactly. And it highlights the fundamental difference in how we perceive and detect network anomalies.
How do you mean?
You see, in a traditional wired industrial cell, if you have latency spikes or packet retransmissions, it is a very obvious anomaly. A cable is either physically plugged in or it isn't.
It's binary.
Very binary. It is sending electrons down the copper wire or it isn't. If the data stops, a red light flashes on a control board, an alarm goes off, and the maintenance tech knows exactly which cable to go look at.
They just follow the wire.
Right. But in a wireless environment, an attacker can mask their malicious activity completely behind the veil of everyday radio instability.
Because wireless is inherently sort of, messy, right? It's just invisible waves bouncing around a giant metal room.
It is incredibly messy. Radio waves are subject to basic physical interference all day long. You have multipath fading, where a radio wave bounces off a steel I-beam, hits a concrete floor, and arrives at the receiving antenna slightly out of phase with the direct wave.
Which effectively cancels out.
Exactly, it cancels it out. You have shadowing from heavy machinery moving around. You have handover issues as a mobile robot moves from the coverage area of one 5G cell tower to another.
So wait, if I am a hacker trying to mess with this factory,
if you are an attacker and you start manipulating traffic, dropping packets, or injecting latency, the system operators looking at the network dashboard might just think, oh, a massive forklift carrying sheet metal just drove past the main antenna.
or like, we're just having congestion issues today.
Yeah, the attacker hides in the ambient, everyday noise of the wireless environment.
Which is terrifying. You can't fight an enemy if you just think it's bad weather on the factory floor.
No, you can't. You're fighting ghosts.
And I was reading through the sources about this specific example of an automotive plant using a private 5G network. And the realization here is that a short disruption does not even need to cause physical damage to be an effective cyber attack.
Right. You don't actually need the robotic arm to crash into a wall.
Because physical destruction is kind of amateur hour, right?
Oh, physical destruction is total amateur hour? The real economic damage is far more subtle than blowing things up.
Right. Because you just need to block the material flow for a moment. Just a tiny interruption triggers a manual workaround. The automated safety protocols kick in, human workers have to step in to reset the system, and suddenly, bam, you have entirely stopped a production line.
And in just-in-time manufacturing, every second counts.
Yeah, if Station 4 stops, Station 5 has no parts. 60 seconds later, the whole plant grinds to a halt.
And stopping a modern automotive production line can cost upwards of tens of thousands of dollars per minute.
Per minute.
Per minute. A 5-minute localized network disruption could cost $500,000. This is why we have to completely reframe our thinking.
Yeah, if you are listening to this and you work in leadership, hear this. Cybersecurity in this context is no longer just an IT problem.
Not at all.
It is not about keeping hackers out of the HR database or protecting company emails. It is the fundamental core of operational uptime. If your radio layer is compromised, your factory does not run, period.
It's that simple.
Which naturally leads me to wonder, if the stakes are literally tens of thousands of dollars a minute, and the radio waves are this fundamentally vulnerable to interference, what exactly are we exposing to the open air?
Ah, the million-dollar question.
Because it cannot just be the shiny new 5G robots. We didn't throw away all the old machines, did we?
Oh, man, I wish we had. I really wish it were just the new natively secure robots.
But it's not.
The reality is much, much grimmer. We are connecting decades-old legacy systems to these cutting-edge 5G networks. It is a massive architectural paradox.
How old are we talking?
Well, you have the most advanced high-speed transport layer ever created, carrying protocols that were designed when the internet was essentially a novelty for university researchers.
I have to admit, I read one statistic in our research notes that genuinely shocked me. Like, I had to read it twice to make sure I wasn't hallucinating.
The plain text stat.
Yes. It said that 65% of legacy industrial control systems transmit their data in plain text.
Plain text?
No encryption whatsoever. You and I wouldn't even log into a basic social media account on our phones without end-to-end encryption. And yet 65% of the systems controlling massive industrial infrastructure, power grids, water treatment plants, assembly lines are just shouting their operational secrets into the void.
It sounds completely absurd to a modern ear. It really does. But you have to understand the historical context to see why it's like this.
Okay, take you back.
You are looking at protocols like Modbus, TCP/IP, Profinet, and EtherCAT.
What are those, mechanically speaking?
They are essentially the languages that industrial machines use to talk to each other. Modbus, for example, was invented in the late 1970s.
The disco era of networking.
Exactly. And when these protocols were designed, they were meant for completely isolated, air-gapped environments.
Meaning they were not connected to the outside world in any way, shape, or form.
Exactly. The foundational assumption baked into the very code was that if you were on the network, you were already authorized to be there.
Because getting on the network was physically difficult.
Exactly. Why would you need a password? To get on the network, you had to drive to the factory, swipe an ID badge, physically walk past a security guard into a locked, secure control room, and plug a serial cable directly into the machine.
So the physical security literally was the cybersecurity.
Precisely. They never imagined a globally connected architecture, let alone a wireless one. So the engineers who wrote these protocols prioritized speed, determinism, and reliability over security.
Because speed mattered more than keeping out phantom hackers that didn't exist yet.
Right. There is no encryption, there is no robust authentication. It is literally sending raw hex codes over a wire.
Give me an example.
Okay, so a command says, turn valve 4 to 90 degrees, and anyone listening on that network sees the exact command in clue text. There is no secret handshake. If the command arrives, the machine simply executes it. It doesn't ask who sent it.
But, and I know I'm playing devil's advocate here, but I know this is what someone listening might be screaming at their dashboard right now. Why don't these companies just update the old machines?
Oh, only it were that easy.
But seriously, if you know the Modbus protocol is fundamentally insecure from the 1970s, just patch it or replace the hardware. Why are we connecting a technological dinosaur to a 5G spaceship?
Because replacing the dinosaur requires turning it off. And we are right back to the boardroom reality we started with. The absolutely prohibitive costs of downtime.
It always comes down to the money, doesn't it?
Always. Upgrading an entire legacy ICS infrastructure requires halting operations. Let's look at major logistics hubs, like marine ports.
Okay.
We are talking about automated straddle carriers, massive ship-to-shore cranes. For a major port, operational downtime can cost $1 million an hour.
$1 million an hour, wow.
So the board of directors looks at a proposal from their security team for a 3-day, 72-hour shutdown to rip and replace legacy equipment.
So that's a $72 million loss of revenue right out of the gate.
Right, and that's not even counting the cascading supply chain nightmares. Ships waiting off the coast, trucks backed up on the highway, they balk at that number, it gets vetoed immediately.
So what do they do instead? Just cross their fingers and hope nobody notices.
They look for a shortcut. They buy a specialized piece of hardware called a protocol conversion gateway.
Which does what exactly?
Its only job is to translate that old, unencrypted Modbus traffic into shiny new 5G IP packets.
So it's just a translator.
Basically, it takes the dinosaur's language, wraps it in a modern 5G envelope, and sends it over the airwaves.
But the inside of the envelope is still just unprotected Modbus.
Exactly. It works functionally, it keeps the factory running, but the underlying vulnerability, the fact that the core message has no authentication, remains entirely intact.
It is the ultimate technical debt. You are just kicking the can down a very expensive, very dangerous road.
Yeah, and the danger of that weak authentication isn't theoretical. We saw exactly how this plays out in the real world with the Mirai botnet.
Ah, Mirai, yes. A textbook, painful example of how devastating default legacy mindsets can be.
It was a wake-up call that a lot of people slept right through.
For those who aren't familiar, or maybe just remember it as that day the internet basically broke, the Mirai case study is wild.
It really is.
You had hackers who who didn't even use sophisticated zero-day exploits. They didn't write some crazy advanced malware. They simply scanned the internet for open telnet ports. And telnet is another ancient unencrypted protocol, right?
Yes, from the 1960s, even older than Modbus.
So they scanned for these open doors, and then they just used a basic dictionary list of default factory passwords.
Yep.
Stuff like admin, root password 12345.
The kind of stuff you'd see on a luggage combination lock.
Exactly. Because nobody ever bothers to change the defaults on these constrained industrial and IoT devices. The maintenance guys just plug them in, verify they work, and walk away to the next job.
They have a quota to meet. They aren't thinking about cyber hygiene.
So the hackers use those defaults to hijack millions of security cameras, industrial routers, and sensors, and build a massive botnet army capable of taking down major internet services through sheer brute force.
Oh man, and the lesson we completely failed to learn from Mirai is that when you bring 5G into the mix, you are drastically expanding the attack surface for those exact types of low-effort exploits.
Right, because everything is wireless now.
Yeah, you are taking millions of new cheap sensors and putting them directly on high-speed networks. And it actually gets worse. It gets even more complicated when you look at how 5G itself is actually being rolled out by the telecom operators.
What do you mean? Isn't 5G just 5G?
Not at all. We have to look at standalone 5G versus non-standalone 5G.
Let me guess. Non-standalone is the cost-saving crutch we are currently leaning on, right?
You nailed it. It is the architectural compromise of the decade.
Okay, lay it out for me.
So a full standalone or SA deployment uses a dedicated, newly built 5G core. It is built from the ground up with a modern 5G security architecture.
So that's the spaceship we actually want to be flying in.
Yes, that's the goal. But the transition to full standalone is a multi-year, highly expensive process for telecom operators.
Because they have to build physical things.
They have to replace the entire backbone of their networks. The hardware, the software, all of it. So to get to market faster, to be able to put that little 5G logo on your phone screen and charge you more for it, most operators use non-standalone, or NSA mode.
Okay, break down how NSA works mechanically, because I think a lot of people assume their phone is just on pure 5G.
In NSA mode, the 5G radio interface, the airwaves, the antennas, are used for the connection to the device, so you get the fast download speeds.
Which is what people care about.
Right, but the actual brain of the network, the routing, the authentication, the management, it is entirely reliant on the old 4G evolved packet core.
Wait, oh wow, so you are selling me the 5G speed, but you are routing all my data through a 4G brain.
Exactly. It's like building a high-speed bullet train, but forcing it to run on wooden tracks from the 1800s.
That sounds like a recipe for a disaster.
It is, because this brings all of 4G's inherited weaknesses, signaling storms, lack of strong mutual authentication in certain layers, right into the 5G era. You get a massive false sense of security. The marketing brochure says 5G, but the security reality is a hybrid mess of older vulnerabilities.
It's like putting a state-of-the-art titanium vault door on a cardboard box.
That is a perfect way to describe it.
Okay, so if we take stock of where we are right now in this conversation, we have logical network vulnerabilities because we are wrapping unencrypted 1970s legacy protocols in 5G envelopes.
Yep.
We have architectural weaknesses because we are relying on non-standalone rollouts running on 4G brains.
Check.
But I think we need to pivot back to the physical reality of the factory floor. Because if the logical layer isn't scary enough, the physical layer, the actual radio waves, is where it gets truly chaotic.
The physical layer is the ultimate shared medium. It is the open air. Anyone can touch it.
And that means we have to talk about the enduring brute force threat of radio jamming.
Oh, jamming. It's the oldest trick in the wireless book.
You know, it is almost funny in a really dark, twisted way.
I know what you're going to say.
You can spend $10 million on zero-trust architecture, advanced software encryption, and AI-driven firewalls. And some bad actor with a cheap, modified software-defined radio they bought online for $300 can just sit in a van in the employee parking lot, flood the local spectrum with RF noise, and effectively become a ghost in the machine.
It is the great equalizer of wireless networks. A guy in a van can take down a smart factory.
How is it that simple?
Because jamming is fundamentally about the signal-to-noise ratio. A power-modulated jammer doesn't need to be sophisticated. It doesn't need to decrypt your data. It doesn't need to crack your passwords.
It's just dumb noise.
It is incredibly dumb noise. It just needs to yell louder than your devices. It drowns them out, and the immediate manifestation of that on the network dashboard is severe, inexplicable high packet loss.
Which, beyond just stopping the data from moving, actually physically drains the energy of these resource-constrained Internet of Things devices, right?
That's the secondary effect, yeah.
Because from what I understand, when a packet fails to send, the device just tries again.
Yes, the automatic retransmission protocols kick in. It assumes there was a temporary glitch.
So they just keep trying to resend the data. They're basically screaming over a loud crowd at a rock concert until they completely lose their voice and their battery dies.
That is a very accurate way to visualize it. And that dynamic creates what we call the weakest link amplification effect.
How does that amplify the attack, though?
Well, the 5G core itself, the servers in the data center might be highly secure and perfectly healthy.
Right.
But the ecosystem relies on these fundamentally insecure battery-powered endpoints, cheap temperature sensors, basic valve actuators.
Things with tiny batteries?
Exactly. When a jammer forces thousands of these devices into a continuous loop of failed retransmissions, they exhaust their batteries, they flood the local cell tower with retry requests, and it destabilizes the entire local 5G ecosystem.
So the noise essentially forces the system to attack itself.
Yes. Now let's take that out of the abstract and apply it to a physical use case. Let's go back to the port terminal.
Okay, back to the massive ships.
Right. If a jamming attack causes a sudden loss of connectivity to an automated crane.
Right. A compromised crane control channel isn't just a technical glitch on an IT dashboard. It is a life-or-death safety incident.
Very much so.
Think about it. You have 40 tons of steel container hanging 100 feet in the air, moving at high speeds. If the telemetry drops because of a guy in a van with a jammer, the crane's safety systems might trigger an emergency stop.
Which you'd think is a good thing, but
But the sudden deceleration causes the load to swing violently. Or worse, the control signal drops right when it's supposed to slow down to set the container down gently, and instead it drops a shipping container directly onto a truck cab.
exactly. The consequences scale instantly from a digital nuisance to a catastrophic physical event. The math stops being about data loss and starts being about human lives.
Okay, I refuse to accept that we're just sitting ducks here.
We aren't.
Good. There has to be a solution.
Yeah.
You can't just tell me the physical layer is entirely defenseless against a guy with an eBay jammer in a van.
No, we aren't completely defenseless, but combating physical interference requires immense, highly responsive engineering.
Tell me some good news, please.
All right, this brings us to some genuinely fascinating research out of Aalborg, Denmark, focusing on rural 5G networks and multi-connectivity strategies.
Okay, what do they do?
They introduced a dynamic algorithm known as Primary Anchored Adaptive Failover, or PAAF.
PAAF.
Yeah.
Primary Anchored Adaptive Failover. Okay, let's unpack this. How exactly does the software algorithm outsmart raw physical radio noise? Because noise is physics.
It comes down to establishing ultra-fast control loop mechanisms that constantly monitor the health of the connection in real time. The PAF system is constantly looking at specific physical layer metrics.
What kind of metrics?
Primarily, it looks at reference signal received power RSRP.
Which is basically the equivalent of the little signal bars on your cell phone, right? The baseline signal strength.
Essentially, yes. It looks at RSRP, and it also monitors uplink transmission power, which tells you how hard the endpoint device is working to push a signal back to the tower.
Oh, I see. Okay, so if the guy in the van turns on his jammer, the background noise floor rises. The device suddenly realizes its whispers aren't being heard by the tower, so it has to scream louder, meaning the uplink transmission power spikes.
Correct. You've got it. And when the PAAF algorithm detects that power spike or a sudden drop in RSRP or an unacceptable spike in end-to-end latency, meaning that packets are taking too long to arrive, it triggers a defensive response.
I'll have ice back.
It adapts. Now, we have to contrast this with the traditional response to understand why it's so cool. In standard, ultra-reliable, low-latency communications, URLC, the traditional way to ensure a packet arrives through interference is full duplication.
Like sending 2 of every...
Exactly. You just send a copy of every single packet over a secondary independent 5G link. You brute force the reliability. If path A gets jammed, path B gets through.
But wait, sending literally everything twice? That sounds incredibly expensive.
It is.
It doubles your bandwidth overhead instantly. If you are paying for data or if you have thousands of robots on a factory floor, that is totally inefficient.
It is horribly inefficient, which is why PAAF is such a massive breakthrough. It uses partial duplication.
Meaning it only duplicates when it has to.
Yes, it only activates that secondary redundant link when the primary link hits those specific degradation thresholds we just talked about. It balances the critical need for ultra reliability with the high overhead costs of full duplication.
That's smart.
Right. The moment the primary link stabilizes, say the jammer turns off, or maybe the robot just moves behind a thick concrete wall that blocks the jammer's signal, the algorithm stops duplicating. It is a dynamic, event-driven survival mechanism at the physical layer.
That is genuinely brilliant. It's like having a backup generator that only kicks on the millisecond the voltage drops, rather than running it 24/7 just in case.
That's exactly what it is.
But here's the thing. Managing the physical layer is just table stakes, isn't it?
Unfortunately, yes.
Because while we are busy dodging jammers in the parking lot and monitoring uplink power, attackers are also evolving their digital strategies. If they can't beat the radio waves, they're going to try to bypass the 5G architecture itself.
That is the grim reality of the cybersecurity arms race. If we look beyond the physical layer to the advanced architectural and future-looking threats, the complexity doesn't just increase, it scales exponentially.
Okay, let's talk about network slicing, because I see this term thrown around in literally every 5G marketing pitch.
Oh, network slicing, the silver bullet.
Right. The idea, as I understand it, is that you can take one physical network, one set of antennas and servers, and slice it into multiple virtual networks.
That's the premise.
So you have one slice specifically tuned for the factory robots, one slice for the guest Wi-Fi in the lobby, one slice for the office IT computers. It is presented to executives as this ultimate fail-safe VIP lane for critical data.
Yeah.
The pitch is, if the guest Wi-Fi gets hacked by someone in the lobby, the robots are perfectly safe because they are in a completely different slice.
That is the theory. And it is a beautiful, very comforting theory. But let me quickly dismantle that false comfort for you.
Please do.
The isolation between those slices isn't a physical copper wire. It isn't a separate router in a different room. It is entirely software defined.
Okay.
Think of it like taking one large physical apartment building and using software to draw invisible walls, creating separate apartments. One apartment is the factory floor, another is the guest Wi-Fi.
Okay, I'm with you. Invisible apartments.
But those invisible walls are managed by an SDN, a software-defined networking controller. The SDN controller is essentially the master key system for the entire building. It dictates who lives where and how thick the walls are.
Oh no, I see exactly where this is going.
If the SDN controller is compromised, or if an attacker exploits a zero-day vulnerability in the virtualization hypervisor separating those slices, it becomes a single point of failure.
The invisible walls just vanish.
Yes, an attacker who gains a foothold in a low-security slice, say, that guest Wi-Fi you mentioned, could potentially execute what is called a cross-slice attack.
So they don't attack the robots directly?
No, they pivot. They pivot through the compromised SDN controller, grab the master key, walk right through the invisible walls, and bring down the mission-critical transport network from the inside.
Wow.
The VIP lane is only as secure as the software drawing the lines on the road.
So much for the VIP lane. That's
Yeah.
terrifying. And since we are talking about software vulnerabilities, we have to talk about the absolute elephant in the room, the weaponization of artificial intelligence.
Yes, we have to talk about AI.
Because the attackers aren't just using brute force password lists like Mirai anymore. They're using AI to poison the well.
Yes. We are seeing a very concerning, highly sophisticated trend regarding data poisoning, specifically targeting predictive maintenance models.
Let's walk through how that actually works, because I hear data poisoning,
Yeah.
and it sounds like, I don't know, a sci-fi spy movie.
It is actually terrifyingly mundane, which is what makes it so effective. Ports and factories use massive AI models to predict when a machine is going to fail.
So they don't have to guess.
Right. The AI monitors the vibration and temperature of, say, a massive industrial motor. It learns the baseline, so it knows when the motor is starting to degrade weeks before it actually breaks. This saves millions in unplanned downtime.
Makes total sense. It's smart.
But what if an attacker gets access to just the temperature sensor feeding data to that AI?
Just the sensor, not the motor.
Right. They don't break the motor. They don't shut it off. They just slowly, subtly inject false data into the training sets. Over the course of 6 months, they alter the temperature reading, telling the AI the motor is running 5 degrees cooler than reality.
So the AI is constantly retraining on this new data, It recalibrates its baseline. It thinks a failing overheating motor is perfectly healthy.
Exactly. The AI will confidently tell the plant manager on a beautiful digital dashboard that everything is fine, right up until the machine literally tears itself apart from heat stress.
That is devious.
And we are also seeing prompt injection attacks against automated systems. If an AI is parsing text commands or logistics manifests, attackers are manipulating the hidden inputs to force the AI into an unintended malicious action, like rerouting a shipment or opening a secure valve.
But on the flip side, and tell me if I am being too optimistic here, I saw a reference in our notes to autonomous SOCs, security operations centers run by AI. Are we really letting AI fight AI on these networks?
We have to. We have absolutely no choice. It is the only way to match the speed of the attacks.
Because humans are too slow.
Way too slow. These autonomous SOCs use AI to monitor the network behavior, and if they detect an anomaly like a device suddenly trying to access an SDN controller it shouldn't, the AI can execute an automated playbook and logically isolate that compromised node in milliseconds.
In milliseconds?
Yes. A human analyst couldn't even click their mouse that fast. It is literal machine versus machine warfare happening invisibly on the network all day long.
That is wild. It really is science fiction happening right now. But while the AI battle is raging, there is a much larger, frankly, existential threat looming on the horizon that we need to address. CRQCs.
Cryptographically relevant quantum computers.
I have to be honest, every time I read about quantum computing, it sounds like pure sci-fi. But the security community treats it like a very real ticking clock. Why?
Because it is the Y2K of cryptography, but with actual teeth.
Okay, how does a quantum computer actually break our security? Break it down for me.
Current encryption, the math that secures your bank account, your emails, and the 5G network, relies on the fact that it is very easy for a normal computer to multiply two massive prime numbers together, but practically impossible to do the reverse.
Okay.
It would take a classical supercomputer thousands of years to factor that massive number back into its original primes to find the key.
Right. The math is just too hard for the processors we have today.
Exactly. But a sufficiently powerful quantum computer, using something called Shor's algorithm, doesn't try every combination one by one. It processes the probabilities simultaneously using quantum states.
Meaning it's insanely fast.
It can factor those massive prime numbers in hours or even minutes. When that threshold is crossed, the mathematical algorithms that currently secure our public key infrastructure, our PKI, will be broken.
And the PKI is what authenticates every device, encrypts every tunnel, and secures every wireless key exchange.
Yes, meaning all that encrypted data traversing the 5G network is suddenly an open book. Every secret command, every industrial blueprint, exposed.
This means we can't wait for the quantum computers to actually be built to fix this. We have to act now.
We absolutely cannot wait. This is why there is an urgent industry-wide need for crypto agility. Organizations must architect their systems now so that when NIST, the National Institute of Standards and Technology, finalizes post-quantum cryptographic standards, companies can hot swap their encryption algorithms without tearing down their entire physical infrastructure.
Because if you wait,
If they wait until the encryption is broken to start upgrading, it will be vastly too late. Attackers are already executing harvest now, decrypt later attacks.
wait, what is that?
They are scraping encrypted data off networks today, just storing it on hard drives, waiting until they have the quantum computer to read it in 5 or 10 years.
Okay, my anxiety is officially peaking.
Yeah, it's a lot. Yeah.
So let's ground this back in a physical use case, because while quantum math is terrifying, we're also seeing emerging risks in the physical world, specifically tied to green energy initiatives.
Yes.
The notes highlight onshore power supply systems, or OPS.
This is a fascinating and terrifying intersection of sustainability and cybersecurity. Let's look at the maritime shipping industry.
Okay.
Historically, when a massive container ship docked at a port to unload, it had to keep its massive diesel engines running just to power the ship's internal systems, the lights, the refrigeration for food, the computers.
Which creates a massive cloud of diesel emissions hovering over the port and city. I know a lot of coastal cities have been fighting to stop that.
Exactly, the pollution is terrible. So the green solution is OPS onshore power supply, also known as cold ironing. It allows these massive 24,000 TEU container ships.
Wait, TEU? I've seen that acronym, but what does it mean?
20-foot equivalent unit. It's how we measure cargo capacity. Imagine 24,000 standard shipping containers stacked on one vessel.
Okay.
It is essentially a skyscraper laid on its side.
Got it. So this massive floating skyscraper pulls into port.
It turns off its dirty diesel engines and it plugs a massive high-voltage cable directly into the port's electrical grid.
Which is great for the environment. Really is. But from a cybersecurity perspective, you are taking a floating city with all of its own complex, likely poorly maintained IT and OT networks and plugging it directly into the critical infrastructure of a major city's smart grid.
You are creating a physical and logical conduit between the ship's systems and the grid.
Oh man.
If a ship has been sailing around the world for 6 months and picked up a malware infection in another port, or if the port's grid is already compromised by a nation-state actor,
The infection can travel across that connection.
exactly. It travels across that high-voltage power connection if the data management links governing the power transfer aren't perfectly segmented.
So we are essentially treating massive container ships like dirty USB drives and plugging them into our city's power grid.
Yes, that is exactly what we are doing. A cyber attack on an OPS system could manipulate billing data, cause massive power surges that fry the ship's electronics, or conversely trigger widespread blackouts across the entire port city.
Okay, let's take a breath and look at the whole board here.
It's a big board.
It is. We have legacy plaintext protocols from the 70s, 5G radio jammers from eBay, cross-slice software attacks in the invisible apartments, AI data poisoning the temperature sensors, quantum computing threatening to break all our math, and container ships acting as massive USB drives infecting the power grid.
It sounds like a bad movie plot when you list it all out.
It does. If you are a chief information security officer listening to this, how can any human team possibly manage this overwhelming matrix of risks?
It requires a complete evolution in how we assess and respond to threats. We have to bring this back to the human element and the reality of the boardroom. The old way of doing things, basic threat modeling, is dead.
What do you mean by basic threat modeling?
Historically, security teams would look at an isolated component. They would look at a single database or a single robot on the floor and say, how could someone hack this specific thing?
Right, and then they put a wall around it.
Exactly, because no component is isolated anymore.
Right.
In a hyper-connected 5G factory, everything touches everything. We must shift to comprehensive threat analysis and risk assessment, utilizing attack graphs.
Attack graphs.
Yeah.
Visualizing the path, like drawing it out.
Yes. An attack graph maps out the entire chain of vulnerabilities. It helps the board visualize how an attacker doesn't just hack one thing in a vacuum, they chain privileges. They step from stone to stone across the network.
Okay, walk me through what privilege chaining actually looks like in a physical factory setting.
Okay, imagine an attacker finds a weak point in the 5G network, maybe a misconfigured router. They use that initial foothold to compromise a navigation electronic control unit, an ECU on a mobile automated robot.
Okay, stop there. What is an ECU?
An electronic control unit. Think of it like a localized lobe in a brain.
Okay.
You have one lobe for vision, one for balance. In a robot, you have an ECU just for navigation, figuring out where it is in the room using lasers. You have another ECU for the actual physical drive motors.
Okay, so the attacker hacks the navigation lobe, but the navigation ECU doesn't control the physical wheels, right?
Correct. So the impact seems low, it just messes up the map. But the attacker doesn't stop there. They use the navigation ECU as a beachhead to move laterally to a gateway ECU. From the gateway ECU, they finally bridge over to the controller area network bus, the CAN bus.
And the CAN bus is?
The CAN bus is the spinal cord. It is the central nervous system that connects all the localized brains together.
So they just step from the guest room to the hallway and then kick down the door to the central nervous system.
Yes. And once they are on the CAN bus, they can send fake nerve impulses to any part of the machine. And the impact diverges based entirely on their goal.
What are their options?
Well, if they manipulate the robot's production speed, say, forcing the motors to run just 10% slower, they cause localized economic damage. The factory produces fewer cars that day. It is a slow bleed that might easily evade detection.
Right, people just think the machine is sluggish.
But if they attack the safety mechanisms, if they disable the proximity sensors that tell the robot a human is standing in front of it, they cause physical injuries or death. The attack graph helps the board understand not just the technical vulnerability of that first router, but the cascading business and safety impacts at the very end of the chain.
That makes the stakes so incredibly clear. And yet the most frustrating part is that all of this sophisticated modeling, all these attack graphs, can be completely undone by simple human error. I was looking at the management of change discipline in our sources. You can spend millions of dollars on zero-trust architecture, microsegmentation, and advanced AI threat detection, and then Bob, from maintenance, decides he needs a better Wi-Fi signal to download a diagnostic manual for a broken machine.
Oh, Bob. We've all met Bob.
So he buys a rogue 5G router at an electronics store and plugs it directly into a secure control panel on the factory floor so his tablet gets better reception.
Or a vendor comes in to service a machine, right? And they ask for a temporary diagnostic link for one afternoon, and the IT team provisions it, and nobody ever remembers to unplug it or revoke the access.
They just bypassed millions of dollars of security architecture because it was convenient for a Tuesday afternoon.
Which is exactly why Zero Trust architectures are mandatory, not optional. The core philosophy of Zero Trust is that you cannot trust a device just because it is physically inside your factory walls or plugged into your local switch.
You can't trust Bob's router.
No. Location is no longer a proxy for trust. You have to continuously authenticate and authorize every single interaction, every single packet. And in the specific context of 5G, this also means leveraging inherent network features like subscription permanent identifier encryption, SUPI encryption.
Okay, let's break down SUPI. Because in 4G, devices broadcast their identity, their MSI number, in plain text, right?
Yes. Every time your phone connects to a 4G tower, it essentially yells its social security number into the air to identify itself.
Which allows an attacker with an MSI catcher like a Stingray device to physically track the movement of specific devices or even specific personnel across a city or a factory floor.
Precisely. SPPI encryption in 5G fixes this by concealing that permanent identity using public key cryptography before it ever hits the airwaves, preventing those physical tracking attacks.
So that's a built-in win for 5G.
It is, but only if the telecom operator and the enterprise actually configure the network to enforce it. The feature exists, but you have to actively turn it on. But I know where you are going next.
You do.
You are going to raise the ultimate pushback here, aren't you?
I am. Because the board of directors is going to listen to everything you just said. They hear zero trust, continuous authentication, heavy cryptography, post-quantum algorithms, and then they're going to look at their production metrics.
Yep.
The trade-off between performance and security is brutal. Every time you encrypt a packet, every time you mathematically authenticate a node, you are adding latency.
I validate that completely. It is the core tension of industrial 5G. It is the unsolvable equation at the heart of the industry right now.
Because math takes time.
Cryptographic operations, especially integrity protection on the user plane, ensuring the data hasn't been tampered with, introduce severe latency. The mathematical hashing operations literally take time for the processors to compute. In an ultra-reliable, low-latency environment where automated operations are measured in single-digit milliseconds.
Adding a delay is a big deal.
Adding a 5-millisecond delay for encryption overhead can throw a high-speed motion control system completely out of sync.
So you are forcing companies to make an agonizing, impossible choice. You either run your factory at real-time operational speed and leave the data exposed to manipulation, or you lock the data down with heavy encryption and accept that your robots have to move slower, costing you money every single second of the day.
That is the exact dilemma. And until lightweight cryptographic algorithms can catch up to the extreme latency requirements of industrial automation, which we are researching but we aren't there yet, it is a risk acceptance conversation that every single board must have.
You have to draw the line.
They have to decide exactly where the line is between an acceptable operational delay and an unacceptable security vulnerability.
And that leads to a deeply uncomfortable hypothetical scenario that I want you, the person listening to this right now, whether you are a plant manager, an IT director, or just someone fascinated by this collision of worlds, to really think about. Imagine a boardroom that faces this exact dilemma. They run the math, they look at the margins, and they decide that the cryptographic latency is just too costly. They choose operational speed over security, deliberately leaving a critical control loop unencrypted to save a few milliseconds. A month later, an attacker exploits that exact vulnerability. They manipulate a safety sensor on the SAN bus, resulting in a massive physical catastrophe on the factory floor. Who is liable? Legally, morally, financially. When you deliberately choose speed over safety, every millisecond of latency you saved was just a door you intentionally left unlocked. That's all for this episode of Cybersecurity Under Pressure. Real attacks, real lessons.
See you in the next chapter.
You have been listening to Cybersecurity Under Pressure. Real attacks, real lessons. Real incidents leave real lessons. Stay prepared, stay critical, and keep following the evidence.